I want to go over two very important ideas that are often neglected when students learn about the work energy principle. So let me quickly review the work energy principle, and then I'll talk about these two things. Before I forget, both of these I learned about from the excellent book and the excellent educators Chabay and Sherwood. The book is Matter and Interactions. I highly recommend. That's my favorite physics book. Okay. The work energy principle says that the work done on a system is the change in energy. That's all that says. And then a lot of people break this into mechanical energy and all this other stuff, but I think it's better to just say work is change in energy. And then we define work as a force over a distance F dot delta R, or magnitude of F, magnitude of delta R cosine theta. And I'm going to only deal with situations where F and dr and delta R are constant, so you don't have to worry about integrating. So let's imagine that we'd use the work energy principle for this falling ball. So I know that I have a gravitational force pulling down on it, like that, and then it moves delta R. And this is I drew the Earth so you could see it, but it's constant force. So the first important thing is this idea of a system. So a lot of times we neglect to define our system. If I define my system of just the ball, then I want to consider what forces do work on the system, not internal forces, only things that either take away or add energy to the system. So you can see here that this force due to the gravitational interaction with the Earth would be an external force, so that it would do work. So if I have that, I would have work as F delta R cosine theta. It'd do some positive work, the ball would speed up. And also I would have a change in energy of the change in kinetic energy. So I know that the ball can have kinetic energy, where kinetic energy is 1/2 mv squared. Now, what if I choose the ball and the Earth as a system? System. Ball plus the Earth. In that case, this whole system, there's nothing adding energy or taking energy away from the system, because it's not interacting with anything outside of it. So in this case, the work would be 0. But the same thing happens. The ball still speeds up. I still have to compensate for that ball speeding up. So in this case, I'd have the change in energy is the change in kinetic energy plus the change in gravitational potential energy. I don't want to derive potentials. I have another video on that. But I mean, that's an important point, is that if I have the ball and the Earth as a system, then I can have this gravitational potential energy, and I do not have work. And that's how we know which to do, whether we have gravitational potential energy or work done by gravity. Now, the most important thing for me in this idea of choosing a system, I think it's important for students to choose a system, but also it avoids the very common mistake that students have. They'll say, oh, that ball has potential energy. Well, really, the ball by itself can't have potential energy, because it's due to an interaction of the whole system. Imagine this was a very massive ball, and I said that ball has potential energy, and it fell down here, and now it has kinetic energy. Well, the Earth could move too. And so we have to include that part of the system to compensate for that. It wouldn't be going quite as fast when it hit the ground, because the Earth moved up towards it. And so the total energy is still, change in total energy is still 0, but it prevents us from saying that ball has potential energy. One object can't have potential energy. There can be a potential energy in a system, but not one object. So that's the first thing. Define your system, and that tells you what does work on the system from external forces, and what kind of energies you have. If I include a spring in my system, then I can have potential energy. If I include some massive object, it can have changes in thermal energy, things like that. Okay, that one I don't think is that big of a deal. The next one is this point particle versus a real system. So let's consider the following case. Here I have a wall. And then I had a ball. Here it is. This is my ball. It's not an actual ball. It's a foam. See, because it's not round. But imagine that this foam is coming towards the wall, and it collides with the wall like this, and it stops. Well, I know that this had some kinetic energy, and then right here it stops right there. It has no kinetic energy. So there had to have been negative work done on the system, right? There had to be in order to decrease the kinetic energy. It had to. So what forces do work on the thing? Well, does the wall exert a force on this? Yes. Does the wall do work? Technically, no. Okay, so remember, let's draw a picture here. And let's draw my ball as this. And so the ball was compressed an amount. This is the ball. Well, an amount, let's say delta S. And then there's a force from the wall, F wall. So we define work as F dot delta R. And in this case, the delta R is this distance. And the force is that. So that's delta R. But the force doesn't actually move. So delta R is actually 0. Because this is how far the force is moved. So delta R is the 0 vector, so work is 0. So then why does the thing stop? Well, I mean, there is some other systems, some other things going on in the system. The system itself has some types of energy. It has some. It's essentially a spring, right? So if you think of it in terms of the system, the real system, I'll call it, of just a ball, then work equals 0. And that's going to be equal to delta K plus delta U, let's call it delta E internal, some internal energy. So there's the kinetic energy decreases, the internal energy increases. And that's one way we can explain why it stops. Because we can't use the work energy principle and that force to say why it stops, because that doesn't do it. Now, if you want to use the momentum principle, that force is applied for a certain amount of time, and that does work. Okay, but in the work energy principle, that force does no work. But we can pretend like it does. So we have the real system. We can also make what's called a point particle system. That's the L, so that's E. In the point particle system, we assume this ball is just a point. And in that case, we use the displacement of the center of mass to calculate the work. So in this case, the work would be F wall delta S. But it's a point mass that only has changes in kinetic energy. So it'll only have a change in kinetic energy. So in this case, this would actually be negative, right? Because the force is that way, the displacement's that way. So it's negative work done, and the change in kinetic energy is negative. So we can look at this situation two different ways. And doing that allows us to find two different things. If I want to find the change in internal energy, I would use the real system because it has a change in internal energy in there. If I know the displacement that the ball moves and I want to find out the force the wall exerts, I don't want to use this because the force isn't even in this system, in this equation. I'd want to use this one. Okay, they both have the same change in kinetic energy. They both represent real things. But by choosing whether we have a point particle system, so, and just to be clear, delta R in this case is how far the center of mass moves. In the real system, delta R is how far F applied. In the point particle system, only delta K. In this, there's other types, delta E other. Okay, so if it's a point particle, it can only have kinetic energy, nothing else. Let's look at another very famous example. And I tried to get this one to work as an actual demo, but it doesn't work very well. Here, this is a yo-yo. And imagine that I pull the yo-yo with the string. And so I'm gonna model what could happen. Two things are gonna happen. It's going to, with a constant force. One, it's going to speed up, and it's going to rotate. And you'll notice that as it does that, the string plays out. So if we think of this in terms of the point particle system, F, and let's say it goes to here. We'll call that delta S. I'm going to write it as a vector. And the string goes like that. So this is point right there. Okay, so it rolled out. In the point particle system, PPS, work would be F delta S, right? Because it's how far the center mass moved, and that'd be equal to the change in kinetic energy. That's it. But it actually does move a lot further. So in the real system, the work would be, let's call this, I need a name for this. How far did F delta, I'll call that delta R. The work would be F delta R. I'm just going to leave it like that as scalar because they're in the same direction. And that would be the change in kinetic energy plus the change in rotational kinetic energy, where, just so you know, K rotational would be 1/2 I omega squared. So as this is pulled out, this real force does work greater than just the change in kinetic energy of the center mass. And that extra force goes in, that extra work goes into the rotational motion of the yo-yo. So again, this is a great way you would do it twice, right? You could do the problem twice. I could use this point particle system to find out how fast the center mass is going. I could use that to find that. And then I could use the real system, once I already know the change in rotation, the translational kinetic energy from this, to find out how much it's rotating. So you'd have to look at how far that thing's pulled. And that's a pretty useful thing. Here's another example, the one that I like a lot. Imagine that I have some stick right here. And I push it right here on the edge. If I push it in the middle, then it's fine, right? Everything's fine. It's going to speed up. Let me rotate this way. It's going to increase in kinetic energy. Imagine there's no friction. But if I push from the side, then two things are going to happen. One, the center mass is going to move, and it's going to rotate. So it's going to rotate, and the center mass is going to move. Again, I can treat this as a point particle system and just look at the motion of the center mass and how far the center mass moved to calculate the work. And then I can look at how far the force was actually applied and calculate the real work. And so two different ways. Here's another example. I'm not solving all these. If you want me to solve them, I will. This is one of my other favorite ones. Here's a chain, a beaded chain. Actually, I have a metal chain too. But as I pull this out with a constant force, what happens? Well, you gotta have it so it doesn't tangle up. So let's do like this. Okay, that's better. So if I pull this with the constant force, what's going to happen? Well, the center of mass of the chain is in not the same location as the velocity of the center mass is not the same as the velocity of the force. So the force will move a different distance than the center mass. So you can use that to calculate the change in internal energy in the chain as you slide it across. Okay, I want to look at one last important thing that does deal with this, and that is the work done by friction. I've talked about this before, and I just want to show you how the point particle system and the real system give a problem with the work done by friction. So if I have a block and I push it with a constant force, just like that, and moves at a constant speed, then how would I use the work energy principle? Well, if that's the case, I could draw this as the free body diagram. mg in, I'll call this Fp for the push, and then the kinetic friction force is equal to that. And I know it's equal because the acceleration is 0. It moves at a constant speed. So I could calculate, if I say my system is just a block, the point, let's just say the system is the block. Is it a real system? Well, that's the problem. Let's just say the system is the block. And then I have 4 things that can do work. I have the work done by the normal force. That's 0, right? Because it's moving this way. The normal force and delta R are perpendicular to each other. So theta is pi over 2. Theta is 90, so the cosine of 90 is 0. This also does no work. It's perpendicular to the direction. So the work done by the gravitational force is 0. The work done by the push, Fp, is going to be Fp times some distance that it moved, and then the work done by friction is going to be equal to negative F friction d. And these are the same thing, so these two works are the same. So the total work net is equal to 0, and that's the change in kinetic energy, which is 0. And everything seems to work out fine. However, it does not work out fine, because as I push this and it slides, and if you were able to look at the bottom with an infrared camera, you would see it heats up. And so there is a change in internal energy of the block. It does increase in thermal energy. So, but even if I put that thermal energy in here, even if I say this work net equals delta K plus delta E thermal, it's still equal to 0. And I know delta K is equal to 0 because it's moving at a constant speed. So that means the change in energy has to be equal to 0. So something's wrong. These two works cannot be equal. They can't be. And in fact, they aren't. The thing is, in the real system, in the point particle system, it is. They're the same, because we're using the motion of the center mass and the frictional force. But in the point particle system, there's no thermal energy, so you're fine. In the real system, what's the problem is that this is not D. That's not D. Okay. The distance that the friction force is applied is not the same as the motion of the block. So you can imagine that this sticks and slips, and so as it moves, it bends the material a little bit, then jumps forward, and then bends and jumps forward. So the distances are not the same, and in fact, the distance the friction is applied is not the same as the distance that the block moves because of the jumping. And that's a kind of complicated thing, but that's the only way we can make this one work. Okay, so in general, it's best just to avoid the work done by friction unless you explicitly say point particle system. Okay, I hope that helps.